Hey everyone, Mr. Andrew here. Today I wanted to talk to you about valence electrons and how Lewis dot structures really show their usefulness. Okay, so we've talked before about valence electrons. Valence electrons are the outermost electrons for any atom. And kind of the way it works is as you go down from like period 1 to period 2 to period 3, these numbers represent how many energy levels a particular atom has. Because we're talking about just the outermost level, when you go down from one period to another, you're actually changing what energy level the valence electrons are in for that particular atom. So, like for instance, lithium, its valence electrons are in energy level 2. But for sodium, its valence electrons are in energy level 3. So let's start out by just drawing the Bohr model. Okay, and let's draw the Bohr model for lithium and sodium. Okay, let's take a look at them. So on this left side, I'm going to do lithium. On the right side, I'm going to do sodium. Okay, so lithium's Bohr model. Well, actually, let's look at its electron configuration first. So lithium's electron configuration is 1s2, 2s1. This means that the first energy level is going to have 2 electrons, and the second energy level is going to have 1 electron. So if we draw the Bohr model for this, just put a little simple nucleus there. We need 2 energy levels, so I'm going to put 2 rings around it. 1, 2, something like that. Okay. And I'm going to put 2 electrons in the first energy level, and then 1 in the second energy level. Okay. So here we can see that lithium has 1, 2, 3 electrons. That matches the electron configuration, and we're good. Okay. Let's do the same thing for sodium. Sodium's electron configuration is 1s2, 2s2, 2p6, 3s1. Okay. So the first energy level is going to have 2 electrons. The second energy level is going to have 8 electrons. And the third energy level is going to have 1 electron. So this one's a little bit bigger, so I'm going to give myself a little bit more room. There's my nucleus, make it a little more round. There's 1, 2, 3 energy levels. Okay. My first energy level is going to have 2 electrons. 1, 2. Second energy level is going to have 8 electrons. Now, I want to put these into this second energy level in a very specific way because electrons want to be as far away from each other as possible. So, the way this works in order to keep it kind of aligned with Hund's rule is you put 1 on each side first, top, bottom, left, and right, and then after that, you pair them up. Okay? It doesn't matter which order you do it necessarily. If you want to just go around in a circle or whatever, I just always do top, bottom, left, and right. That way it looks a little bit more clean. Do my little bookkeeping right here. The only electron left is this one in the third energy level. So if we look at the total electrons, let's draw a little, actually I'll just put total electrons right here. If we look at the total number of electrons, lithium has 3 and sodium has 11. Okay, so there's not a lot of similarities here. But if we look at the valence electrons, which are just the outermost electrons. We just want to look at how many electrons are in the outermost ring. For lithium, there's one valence electron. And for sodium, there's also one valence electron. You can see them right here and right here. Okay? So even though they have a different number of total electrons, they have the same number of valence electrons. And this is important because them having the same number of valence electrons means that they also have similar properties to one another. Okay? So we wanted a shorthand way of representing this because I picked two of the simpler elements. I picked lithium and sodium. But if each one of these periods represents adding an additional ring to this, by the time you get to something like rubidium or cesium, your Bohr model can be really, really complicated. Let me just add a little tag. This is the Bohr model. This is the electron configuration. Okay. So instead, scientists created something called the Lewis dot structure or Lewis structure. And the Lewis dot structure is basically just a shorthand way of representing how many valence electrons a particular atom has without having to put all of these rings in the Bohr model. So here's how you write the Lewis dot structure. You put the name of the atomic symbol in the middle, and then you just put one dot around it for each valence electron. For lithium, it's got one, so I'm just going to put one dot right here. And that's it. For sodium, the symbol is Na. And again, it's got one valence electron, so I'm just going to put one dot. Now, these Lewis dot structures can account for any number of valence electrons, but you're never going to have more than 8 valence electrons. Okay? That's because all of these D block elements right here in this middle chunk, these are the D block. And all of these in the F block over here, these are called the F block elements. Their electrons can never be valence electrons. So the most valence electrons you're ever going to have are 1, 2, 3, 4, 5, 6, 7, 8. Okay? Now, when you're drawing these Lewis dot structures, you have to put the dots in a very specific order. Okay? So let me do one that's a little bit more complicated. Okay? Let me clear off some of this. There we go. Okay, let's say I wanted to do the Lewis dot structure for sulfur, for instance. Okay. The Lewis dot structure would have the atomic symbol S. Okay. And then sulfur has 6 valence electrons. So that means I need 6 dots around this S. So I'm going to do top, bottom, left, and right. So we got one on each side first. This is in line with Hund's rule, which says that electrons are unpaired first and then they become paired. So once you have 4 dots, you've got 2 left because I need to get to 6. So I'm going to put one right here, and I'm going to put the other one right here. Okay. Now, it doesn't actually matter where you put the pairs as long as you have two paired and two unpaired. So that means that this is the same as something like this. It's the same as something like this. Any of these is fine. And there are others. But any combination of two paired and two unpaired is fine. All of those are accurate. Okay? So this means that the most complicated one, like let's say you have something like argon, the most complicated one would have 8 dots. 1, 2, 3, 4, 5, 6, 7, 8. Okay? Something like that would be the most complicated one. Okay? So hopefully this helped you out. If you have any questions, feel free to stop by and see me anytime you need.